So I think next week I will start chapter 18. I believe next Friday is a holiday. Easter, Good Friday. So I think because I'm running behind, I didn't expect to run behind, but I'll give you a recording to watch for extra credit. So I've been getting emails about possible extra credit, so here's another opportunity to get some extra credit that will help boost your grade. And then we'll follow that up with the last week. Whatever I can get done with chapter 18 is whatever I'll get done, and that's what I'll test you on. All right, so let's go ahead and get started here. Predict and then calculate the standard entropy change for the following reaction. All right, let's predict first. So remember, entropy means disorder. So let's predict what we see here. We have 2 gas plus 1 gas, so that's 3 gases going to 2 gases. So 3 gases going to 2 gases. Is that more order or more disorder? This will be more order. Okay, going from 2 going to 3 is more order. Okay, so what will the delta S be? Positive or negative? It will be negative. Very good. Okay, so the delta S is going to be negative. But what is the value of this delta S? Okay, it's negative. But what will be the value of that? So we'll utilize this equation. This is the standard state. Okay, standard state conditions. So we'll use this table here that's provided to us on page 4. All right, it's sum of the products minus sum of the reactants. Sum of the products minus sum of the reactants. Okay. So we have a product here, 2 CO2 gas. So let's look up CO2 gas here. It's 213.7. That's for 1 mole. But how many moles do we have in the problem? So it'll be 2 times 213.7. Okay, joules over mole Kelvin. Okay, minus, okay, I want you to put a big bracket here. Let's do the reactants. We have CO. CO is 197.7. Okay, that's for 1 mole, but how many moles do we have? How many? 2 times 197.9 joules over mole Kelvin. And then we have oxygen gas. So what is oxygen gas? I'll give you these values. You can look them up in a textbook. Oxygen gas is 205. Okay, 205. That's for 1 mole. How many moles do we have? 1. Okay. So make sure you distribute out that minus sign. Okay. So where students really mess up is just doing the calculator. Okay? So I'll just save some time and give you the answer. And the answer that I got is minus 173.47 joules over a mole Kelvin. Okay, look, you guys said it was minus. You said it was minus, Sam, and she's right. It is minus. It's minus 173.47. Okay, this is under standard state conditions. Okay, so can we do this on an exam? Okay, do we know how to do this on a test or an exam? Let's do a couple of more problems here. Okay, let's predict one more time. We have 3 gases. 3 O2 going to 2 O3 gas. So positive or negative, what would you predict the delta S being? Is this more order or more disorder? 3 gases going to 2 gases. So what is more order? Negative. Okay. So we'll do sum of the products minus sum of the reactants. Okay, so we have O3 gas. What's O3 gas?
You're just looking at the coefficient, right? It's not the O2 or O3, because that counts as like one entity, correct?
But there's two entities. So that's why you take the O3 and multiply it by 2. So this is a number that you'll get from a textbook, or you'll be given. And then, so 238. And the equation is sum of the products minus sum of the reactants. So this is for 1 mole. But how many moles are there in the balanced equation? 2. So this is why you have to multiply it by 2. Okay, that's the only product, so you're going to put a minus sign. Sum of the reactants, there's only one reactant, that's O2 gas. What is its value for standard entropy of formation? 205, that's for 1 mole. But how many moles do we have? So you have to multiply it by 3. So doing this on my calculator, I am getting, you guys predicted it to be negative, and I predicted it, and the number from my calculator is negative 137.45 joules over a mole Kelvin. All right, how about this one here? We have a solid going to a solid, liquid, and gas. Solid going to a solid, liquid, and gas. Is that more order or more disorder? More disorder is the right answer. So what will that make our delta S? It will make our delta S positive. Okay. So here we have 3 products. We'll do Na2CO3, which is 136, and that's for 1 mole. And how many moles do we have? 1. Okay, H2O liquid, 69.9, that's for 1 mole. How many moles do we have? 1. You just got to make sure your equation is balanced. CO2 gas is the final product. What is CO2 gas? 213.7. Okay. I want you to put a big minus sign here. NaHCO3 is 102.1. This is for 1 mole, but how many moles do we have? 2. Okay, we got to multiply it by the coefficient. Okay, really that's what this equation is telling us here. Okay, you have to multiply it by the stoichiometric coefficient. Alright, so don't forget to distribute the minus sign, and then on my calculator we predicted it to be positive, and when I did the calculations I got 215.3 joules per mole Kelvin. And on my calculator it looks like it is indeed positive, and it is positive because we have a solid going to another solid, a liquid, and a gas, so that makes it more entropy. Okay. So can we do something like this on the quiz or a test? Alright, so something like that on the exam. I'm not going to talk too much about this, but we do have an equation here, so I'll let you study this independently. I'll just briefly touch upon this. So the entropy of the surroundings, the disorder of the surroundings. What is the surroundings? It's everything. It includes the test tube. It includes the beaker. Okay? It includes everything outside. So sometimes we call the surroundings the universe. Okay, what is the system? Okay, it's whatever is inside the test tube, whatever is inside the beaker, the actual reactants. So we have the minus enthalpy, we divide that by the temperature, and we get the entropy of the surroundings. Okay? So we can look and see if you're exothermic, okay, what does that do to the entropy of the surroundings? If you're endothermic, what will that do to the disorder of the surroundings? All right, so an equation here, I'll give that to you, but to be honest, I probably won't test this. You may see this later. if you continue and further study this. So just want to get you exposed to that. All right, let's go to page 6 here. Here's another thing. I just want to expose this to you guys. I'm probably not going to test you on it. This is called the third law of thermodynamics, and is the entropy of a crystal at absolute zero. Absolute zero is 0 Kelvin. Okay, if you can get to such a low temperature, and if you're a crystal, so a crystal is very ordered. You know, diamonds are very ordered. Any type of thing, you know, these types of metals are very, very ordered. They have a very strict lattice structure. In fact, if you look at them under the most powerful microscope, they're a lattice. And the way lattices are arranged is with what's called a unit cell. So the unit cells are perfect in a crystal. So this is like, the entropy is like very, very ordered. You can get it to such a low temperature where the molecular motion is stopped or ceases. That means the entropy will be 0. Okay, so a pure crystal will have, at 0 Kelvin, will have no entropy. All right, so this is what the third law of thermodynamics states. All right, again, something I just want to tell you guys, but you may not see this on an exam. Okay, 0 Kelvin, 0 Kelvin. All right. Lastly, let's talk about the final thing here, and this is Gibbs free energy. So I want you guys to know that this is the energy available to do work. Okay, what is work? To move a muscle, to, you know, light a light bulb, okay? To do something, okay? It doesn't just go wasted. So we call that work energy, and delta G is energy available to do work. Gibbs free energy is energy that could be harnessed or captured. It's not lost as heat. It's not lost as heat. So we have a couple of equations for you. First, it's the same as the delta S. Okay, so this is the delta G of the reaction. This is called standard state. Okay, if you see that little O, that not symbol, that is standard state. So it's the sum of the products minus sum of the reactants. We'll give you these values. Okay, they're usually in the back of a textbook. And then I mentioned this before, a delta G is the final judge. Okay, it really determines whether the reaction is going to be going to products or not. Okay, and if your delta G becomes negative, even if it's at standard state, okay, so we have to distinguish between delta G and then delta G naught. This is any condition. This is standard state condition. A standard state. Okay, so if your delta G is negative, this is an exergonic reaction. Okay, if your delta G is positive, this is an endergonic reaction. Okay, which way will an exergonic reaction face, product or reactants? Okay, so it will, exergonic reaction will release energy, and if it releases energy, it will favor the products. Okay, where will an endergonic reaction favor? Okay, delta G is the final arbiter. Okay, it determines whether the reaction will go or not, will go to products or not go to products. So if it's endergonic, it requires energy to fulfill the reaction. So it's going to favor the reactants. This is a reaction that will not happen. And then if delta G is 0, then It does not favor products. It does not favor reactants. Okay. Why is this? This is so old. This is on its last legs. I hope the university buys another one, but I doubt it. All right, so delta G is delta H minus T delta S. So the delta G takes input from two other thermodynamic parameters. So if you take thermo, you'll learn about enthalpy, which is heat flow, and then entropy, which is disorder. Okay, so the easiest things to recognize is that if you're enthalpically favored, you're exothermic. You release heat. If you're entropically positive, you go to more disorder. Releasing heat, more disorder. That is, regardless of your temperature, you'll always be spontaneous. Okay. Okay, if your delta H is positive, this is called an endothermic reaction. Endothermic. Okay, requires heat. Okay, not favored to go to products unless you provide the heat. A reaction that's entropically not favorable will be negative, more order. To have more order, you have to put in the work. So regardless of temperature, this is a reaction that will never happen. Okay, you don't have to manipulate the temperature to make it go. Okay. Right. The things here that are kind of tricky is if you're enthalpically not favored, this is endothermic, but you're entropically, okay, everyone listen, entropically favored, so not favored and not favored. What you want to do is you want to raise the temperature to get this negative. You want to raise the temperature to get this negative. Okay, so you raise the temperature to get it negative. Okay, to get the delta G negative, right? Delta G negative means the reaction is favored. Okay, what about a reaction that is enthalpy? Enthalpy favored, entropy not favored. Okay, more order is not favored. You need to put in the work. But enthalpically, it releases heat, so that favors it in terms of enthalpy. Okay, to get the delta G minus, or to get the delta G negative, you have to lower the temperature. See, the thing you need to do is get the delta G negative to make the reaction go to products. But if you're enthalpically favored, entropically disfavored, you lower the temperature. You lower T to get this negative. Okay? So that's how this works. Okay? These situations, regardless of temperature, you can make the reaction go or not go. Temperature doesn't play a role. Here, temperature does play a role. Okay, temperature plays a role in what? Okay, making the reaction go to products. All right, we have an equation here. Okay, I'll give you this equation on the exam. So we have delta G equals delta G naught plus RT natural log of Q. Q, we use Q and compare it to K. Okay, we use Q and compare it to K. So if your Q is greater than K, the alligator jaws point to the reactant side. Okay, so the equilibrium shift to the reactant side. Okay, if Q is less than K, we're going to put Q first. The alligator jaws point to the product side, so this is going to shift to the product side. And then finally, if Q is equal to K, it's not going to shift anywhere. You are actually at equilibrium. Okay, at equilibrium, your delta G is equal to 0. Okay, delta G. Not delta G naught. Not delta G standard state, but delta G is equal to 0. All right. So notice things about this equation. One thing about this equation is that to get the delta G Gibbs free energy change at non-standard state, what do you need? You need the Gibbs free energy change at the standard state, okay? Plus R, which is a constant, and then T, which is temperature, okay? So you need the delta G at the standard state in order to calculate delta G at non-standard state. All right, here's another equation I will give, okay? Basically, this is plug and play, okay? At standard state, this is equal to 0. Okay, when you're at equilibrium and there's no shift, this was equal to 0. And then when you're at equilibrium, you're not at Q, you're at K. Okay, so this is at equilibrium, where the reaction is settled, either this way or this way. The reaction has settled at equilibrium, and this is the equation you will use. All right, so everything corroborates in thermodynamics. Okay, everything corroborates. So if your K is greater than 1, your equilibrium constant, that means you'll have more products than reactants. Okay, imagine if I gave you $1 million. Are you moving forward or backward? Forward for most people. So if your K is large, you're moving forward. If your K in an equilibrium reaction is large, it's products over reactants, no solids, no liquids. That means you're favoring the products. It also means your delta G is negative, which we call then exergonic reaction. Remember? Exergonic. Okay, the natural log of K is positive. Okay, if your K is really, really small, products over reactants, that ratio is small, it will favor the reactants. The delta G is positive. Delta G is positive. We call that an endergonic reaction. So basically what we're doing is we're relating the energy flow, Gibbs free energy, to the equilibrium, okay? In terms of which will be favored, products or reactants. All right, these last two problems will illustrate this, and then all right, calculate the equilibrium constant Kp for this reaction. Okay, so calculate the equilibrium constant Kp. I see here standard state free energy values. So equilibrium constant Kp, this is the equation we'll use. Okay, I'll give this to you on the test. You don't have to memorize this equation. So how will we calculate delta G naught of this reaction? Okay, it's going to be the sum of the products minus sum of the reactants. Okay, so we have 3O2 as our product. The formation delta G is 0, and that's for 1 mole. How many moles do we have? 3, so we're going to multiply this by 3. So multiply this by 3. Okay, I want you to put a big bracket here because some of the reactants, this is 163.6, so I got these from a textbook. And that's for 1 mole. How many moles do we have in this balanced equation? So 2 times 163.6. I'm getting, when I do this, minus 327.2 kilojoules per mole. All right, let's go ahead and substitute that in here because we're trying to solve for Kp here. I'm going to convert this to joules over a mole, okay, because R is in joules over a mole. Okay, I'm going to convert this to joules over a mole, which makes this minus 327,200 joules over a mole equals minus R. I'll give you R. T, what is T here? Okay, the T is our temperature, and that's 25 degrees C. But let's convert it to Kelvin, and that will make it 298 Kelvin. And then natural log of Kp. Alright, so natural log of Kp is equal to, so K has no units. That was one of the questions on the exam. So K will have no units. Joule per mole cancel, Kelvin, Kelvin cancel. It's going to be minus 327,200 divided by minus 8.314 times 298. Okay? So this is going to equal to natural log of Kp. Alright, so do you know how to solve for Kp here? Okay, we will take E. Okay, E of this value to give us Kp. Minus 327,200 divided by 8.314 times 298 is minus 132.06. I'm going to take the inverse lateral log of that, which is E, right? E, and I'm getting, let me try this again here. 327,200 divided by 8.314 times 298. Okay, and then inverse log of that, which is E. Inverse natural log is E. And yeah, this is very, very large, 10 to the 57. Okay. Just want to bring your attention to this, so let's forget about the math for a second. This is exergonic. It will release free energy. Okay, so from a thermodynamic perspective, this releases energy. Okay, what do you know about this value of K? Okay, 10 to the 57 is huge. Okay, it's greater than $1 million, even though this has no units. So what do we say about a large K? It definitely favors the products. Okay, products over reactants. Okay, no liquids, no solids. What do we know about this negative sign? It definitely favors the products. It actually favors the products and releases energy on top of that. So you know that favors the products. Right, so these two corroborate. The equilibrium products over reactants corroborate with the energy. Our last problem, which is of this chapter, before we go to one more, is this one here. All right, the Kp of this reaction, N2 gas plus 3H2 gas goes to 2NH3, is 4.3 times 10 to the minus 4 at 375 degrees C. In one experiment, the initial pressures are these guys. So this is non-standard state. Okay, how do I know it's non-standard state? Because if it was standard state, it would be 1. It would be 1 atmosphere. Okay. And And if it was standard state, it would not be such a high temperature. Standard state is 25 degrees C. So this is non-standard state, and they want to know the delta G. Okay, this is not delta G, the reaction. Okay, but delta G under these conditions. Okay, so the equation we will use is this. Right, I'll give you that equation on the test. Okay. All right, let's first calculate Q here. Okay, Q is products over reactants. So we have the pressure of NH3. Okay, we will square it, divided by the pressure of N2 times the pressure of H2 cubed. All right, the pressure of NH3 squared is 4.4 times 10 to the minus 3 atmospheres. Okay, divided by the pressure of N2, 0.86. Pressure of H2 is 0.4. Okay, we will cube that. All right, when I do this on my calculator, just to save some time, I got 3.52 times 10 to the minus 4. Okay. So this will be our Q. Our K in this problem is 4.3 times 10 to the minus 4. Okay. So it looks like it favors the right. This favors the products under these conditions. Okay, non-standard state conditions. Non-standard state pressure and non-standard state temperature, 375 degrees. All right, so now let's calculate the delta G of the reaction at standard state. It's going to be sum of the products. So we have NH3. Okay, that's for 1 mole. How many moles do we have? 2. Okay, I want you to put a big bracket here, minus and a big bracket, minus sum of the reactants. So delta G for hydrogen is 0. That's for 1 mole. How many moles do we have? 3. Okay, plus N2. That's for 1 mole. How many moles do we have? 1. Okay, so 2 times negative 16.3 minus 0, minus 0. Okay, don't forget to distribute the minus sign. This gives me minus 32.6 kilojoules per mole. Okay, I'm going to convert that to joules per mole. Okay, because my R is in joules per mole. Okay, let's plug that in here. Minus 32,600 joules per mole plus R, 8.314 joules per mole Kelvin. T, what is our T here? Yes, let's convert that to Kelvin by adding 273 and giving us 648 Kelvin, natural log of Q. Okay, I'm just plugging it into this equation. And the Q here is 3.52 times 10 to the minus 4. All right, so the kelvins cancel. Can we do this on our calculator? First, I'll do natural log of 3.52 times 10 to the minus 4. natural log of that. What's going on here? Natural log of 3.52 times 10 to the minus 4 times 648 times R, which is 8.314. Okay, that's minus 42,840 plus a minus 32,600 plus a minus 32,600. I'm getting minus 75,440 joules over a mole, okay, which is exergonic. Okay, I can divide it by 1,000 and get it to be minus 75.4 kilojoules per mole. And this is exergonic. Okay, what did we say an exergonic reaction favors? Products. Okay, what does the equilibrium tell us? The equilibrium shifts it to the right, which is products. Okay. So that is a wrap of chapter 17. We'll have a review to go over these concepts when that time comes. All right. So I am going to start our last chapter, which is chapter 18 here, in the last 7 minutes or so of class. I'm going to start with an intro. Okay. And the last chapter in this class has to do with electrochemistry. So I'll just give an intro, and then we'll get into the nitty-gritty next week. Okay, have you guys heard of a battery? Okay. Okay, so it turns out we can make a battery out of chemicals. Okay. Hence the term electrochemistry, which is a joining of the word electricity and chemistry. So we measure batteries in volts. Okay, voltages. Okay, volts. So you can get a voltage from two chemicals. Okay, how do we do that? Okay, how do we make a battery? Okay, so a battery is two parts. Okay, it is a cathode and it is an anode. Okay. Now, to make a battery, we are exchanging electrons. Okay, we are exchanging electrons, not protons. This is not acid-base chemistry. Electrons. So what is an electron? Okay, E minus. Okay. Okay. Or it could be, we can exchange 2 electrons or 3 electrons. It doesn't matter, but this is an electron transfer process. Okay, we call this an oxidation reduction reaction, also known as a redox reaction. Okay, when you transfer electrons, it is a oxidation reduction reaction. For every giver, there's a taker. Okay, for every giver, there is a taker. Okay, so we need a couple. Okay, this is called a redox couple. So let's have a redox couple between myself and Susanna. Okay. So this is an exchange of electrons. So the cathode, okay, have you heard of this? Red cat eats an ox. Okay, reduction occurs at the cathode. Red cat, reduction, cathode. And ox, anode oxidation. Oxidation at the anode. Okay. So the 2 parts of a battery are a cathode and an anode. The cathode is the terminal where reduction happens. Okay. So what is reduction? Okay. Have you heard of Leo Gurr? My friend, his name is Leo Gurr. Leo Gurr. So what happens at the cathode reduction? So what is reduction? See, this is all a transfer of electrons. 1 or 2 or 3 electrons. So a reduction is where you gain electrons. You gain electrons at the cathode. In other words, you get reduced at the cathode. At the anode, you lose electrons. Lose electrons, oxidation. Okay. So the two parts of a battery are the cathode and the anode. Okay. You gain electrons at the cathode. Red cat eats an ox. You lose electrons at the anode. All right. So let's say Susanna and I are a partner, a redox couple. I'm going to we'll do a 1 electron transfer reaction. I'm going to give 1 electron. I lose my electron. When I lose my electron, I become positive. Okay, I sacrifice my electron. Who's going to take it? We need a couple. Susanna will take that electron. This is a 1 electron transfer reaction. Okay, Susanna takes that electron and becomes herself negative. Okay, so what is the net of this reaction? This electron in the product side cancels this electron on the reactant side. So our net redox reaction is VJ plus Susanna in black ink. Okay. She gains an electron. This is a 1 electron transfer reaction. And I lost that electron, I become positive. So I lost an electron. Do I become oxidized or reduced? Where does oxidation happen? In the anode or the cathode? So if we were a battery, I would be an anode because I get oxidized. What would Susanna be? Is Susanna losing an electron or gaining an electron? She gained 1 electron. Cathode is where reduction happens. She is become reduced. Okay, so Susanna has become reduced. I have become oxidized. If we were a battery, she would serve as the cathode, and I would serve as the anode. Okay, so just replace VJ and Susanna with actual chemicals, and then we have the focus of this chapter, which is electrochemistry. Final thing here, voltages. Do we deal with positive voltages or negative voltages? When you go to Walmart, are you buying 9-volt batteries or negative 9-volt batteries? Okay, this makes sense. Okay, 9-volt battery, 12-volt battery. Okay, so if you have negative voltage, are you a battery? You're a dead battery. So will that reaction go if it produces negative voltage? So if it's a negative voltage, that reaction will favor reactants. If you're positive voltage, that electrochemical reaction will favor what? Favor what? Products. Positive voltage means it favors the products, okay? All right, so have a good weekend. I will see you all as we wrap up the class. Again, next Friday, I'll give you some extra credit if you watch this review. Okay?
And homework is for chapter 17 is due today.
Whenever I posted it on Canvas.
Okay,
But
so
give or
today.
take a day, it's fine. I won't look at Canvas. But if you turn it in tomorrow, that's okay.